Okay, I'd like to thank Libor and Jairo for giving me the opportunity to discuss our results on ruthenium dioxide. And we do photoemission spectroscopy to detect the time reversal symmetry breaking in this material. So let me start with our team. So what you can see here is our photo. This is not going to work anymore. So our team here in Mainz, where we do photoemission spectroscopy, and we are doing also some technical developments on this method. For the ruthenium dioxide, I cooperated with a group of Gerhard Jakob, who managed to fabricate thin films of ruthenium dioxide in a certain surface orientation. And we cooperate with Jairo Zonova and Libor Smykel on the theory, also on one-step photoemission theory with a group of Jan Minard. For the beam times in the results, I had help from Quinn Nguyen and Dima Kutnyakov, Niels Wind, Wendhaus, and Scholz and Hösch. And we discussed a lot with Thomas Jungwirth about the results. So this probably you saw already many times. So this is the idea of altermagnetism. It combines properties of ferromagnets and anti-ferromagnets. So in ferromagnetic materials, you don't have compensated moments. You have a finite magnetization. For anti-ferromagnets, it is opposite. You will have compensated magnetic moments, and altermagnets also have compensated magnetic moments, so no external magnetization measurable. For the spin polarization, you know that every ferromagnet has a finite spin polarization at the Fermi edge, and or for certain bands. And for antiferromagnets, this is not the case. The spin polarization is always compensated. And for altermagnets, it's the theory is supposed to have also in certain momentum directions a spin polarized bands. Now the question is about magnetic circular dichroism. For ferromagnets, magnetic circular dichroism is very well known. For antiferromagnets, it's also known that circular dichroism does not exist. So our question is whether we have magnetic circular dichroism for altermagnets, which would be a direct test for the violation of time reversal symmetry. And of course, we expected that. And then we do the experiment on ruthenium dioxide. Ruthenium dioxide is for us now the workhorse material for altermagnetic properties. Ruthenium dioxide has this crystal structure here in real space, and in reciprocal space you have this Brillouin zone here. And in the most interesting direction in reciprocal spaces from the gamma point to the M point on this gray plane that you see here. So from the gamma to the M point, calculations show that you would have exchange splitting of spin polarized bands. So red stands for spin up and blue for spin down electrons, and you see that you can hear fairly large exchange splitted bands to have in ruthenium dioxide. So, but we do not measure directly spin polarization. We measure magnetic circular dichroism, which is way more easy. So what has the magnetic circular dichroism to do with the spin? So this can be explained most easily here by Wolfgang Kuch and Klaus Schneider's work, which is already 20 years ago. So in these materials, you have exchange splitting, as I've explained already. So the exchange splitting splits states with spin up from spin down states. Blue stands for the spin direction. So the exchange splitting splits the blue spin up from the other blue spin down vectors. Now you have, in addition, spin orbit coupling. The spin orbit coupling splits the case where the orbital momentum is parallel to the spin from the state where the two vectors are antiparallel to each other. Usually in this transition methods, the spin orbit coupling is quite small. but there's a finite splitting. And the splitting happens for spin-up electrons and for spin-down electrons. Now, if you shine circular polarized light on it, the circular polarization acts not on the spin, it acts on the angular momentum. That means if you have right circular polarized light, for example, you will excite states which have a red angular momentum spin-up vector. This occurs here, and this refers to the black line. So you expect intensity as shown by the black line. If you go to left polarized light, you have the dotted line here. So you expect intensity here where you have the red spin down, red angular momentum down vector here and here. Now you take the difference, and the difference does not vanish. And you can see in the difference you have this characteristic spectrum, which is then called magnetic circular dichroism in photoemission. So how do we measure? So in our case, we measure in such a way that we use the 110 surface of ruthenium dioxide. In the 110 surface, you have the magnetization vector of the moments show parallel to this 1001 direction. So the magnetic moment show horizontal here. 110 is the surface normal, and we shine the light perpendicular to the parallel to the magnetic moment, of course. So, and then this looks like this here. The experiment, we shine circular polarized light on the sample. We detect the photo-emitted electrons with this instrument here. And then we have a two-dimensional detector here, which measures the parallel momentum of the excited photoelectrons. And it is time dependent, so we also can use this time of flight method to measure the energy of the excited photoelectrons. And with that, we come to this result here. So along the M gamma M direction here, we see the dispersion in the intensity of this band. And we measure this intensity for circular left and right light and take the difference divided by the sum, and this we call asymmetry. Blue means negative asymmetry, red means positive asymmetry, and you see here that there is a characteristic dispersion of this asymmetry. If you go along the Fermi edge here in this direction, you have this characteristic blue, red, blue sequence, or if you look at the gamma point, also you have the red, blue, red asymmetry. And this is in fact also consistent with theoretical calculation of the one-step photoemission intensity as done by Jan Minar's group, as you can see here. So you see also here this characteristic blue, red, blue sequence and or red, blue, red sequence along the gamma line here. The asymmetry has two components. The asymmetry always has this magnetic circular dichroism, which should be even in both directions here. So for the gamma M direction to the left and gamma M direction to the right, you expect the same behavior for the magnetic circular dichroism. On top of that, you have also the circular dichroism in the angular distribution of photoemission, which is expected to be anti-symmetric to the left and to the right. And you can decompose the experimental results into these two components here, magnetic circular dichroism and dichroism in the angular distribution. And you see that both very nicely fit to the theoretical calculated results. So how does that come about? We can also measure, of course, at the Fermi surface here the intensity distribution. This was a gamma M direction, which I showed you before in the dispersion mode. This is now a constant energy map. So you see here the cut through the Fermi surface, if you want, in this gamma MA plane. And we also experimentally measure this asymmetry at this Fermi surface. Before I showed you the gamma M line, and you see this blue, red, blue sequence here, which you saw before. So now we try to decompose that into components, where the circular dichroism in the angular distribution is in the end only a non-relativistic atomic orbital effect, if you want. Because if you have the three vectors, incoming photon beam, the surface normal n, and the emission angle of the, or emission momentum of the emitted photoelectron, if these three vectors are non-planar, you have a certain chirality in the system here. So if you put a mirror, you get the opposite chirality here. In our case, the mirror plane is given by the incoming photon beam and the surface normal. And that's why our mirror plane is here along this gamma z line. And we expect that we have an anti-symmetric behavior with this idea here from up to down. And we can decompose the experimental result into the CDAD and in the symmetric MCD effect, as you can see here. Now we can somehow combine the information on the intensity and on the asymmetry in this figure here to see where actually our asymmetry is connected to the bands, and this is a calculated MCD result in the one-step photoemission calculation. So we have the wrong direction. So we have more evidence for that. I mean, for a ferromagnet, you know, if you turn the ferromagnet upside down, you change the polarity. We can also do that here. So instead of applying a very large magnetic field, we just rotate azimuthally our sample. So we have the same sample looking on it. We see two intensity maps here for sigma plus and sigma minus. We calculate the asymmetry, the CDAD, and the MCD, so the magnetic circular dichroism, which should not show up for an antiferromagnet and is indicative for time reversal symmetry breaking. Now we turn the same sample by 180 degrees, repeat the experiment under the same geometry, all experimental conditions are the same. And what you then observe is the asymmetry largely looks not very much different, and that comes because it is dominated in these regions here mostly by the circular dichroism in the angular distribution, which is by crystal symmetry not expected to change if you rotate the sample by 180 degrees. But the magnetic circular dichroism, which we calculate here, changes obviously its sign, and that is a clear hint that we have here a kind of magnetic circular dichroism which fulfills the symmetry behavior that you expect also for a ferromagnetic material. We can also calculate that system here completely. Jan Minard did that. So for the Néel vector being parallel or anti-parallel to the circular right polarized light, you expect here this behavior for the asymmetry CDAD and MCD. And you can see how this is in the end connected to the spin. It's not a direct connection, but there are in the calculation certain similarities. For example, this, if you go look around in the center row, you have here this blue up and down and the red color left and right. And this is somehow similar to the blue color you see here also for the spin. So the magnetic circular dichroism in this case is indicative for the spin direction of the bands. And of course, if you flip here the direction of the Néel vector, you do flip the spin, obviously. You also flip this MCD. What you do not flip is the CDAD, so this fits experiment and theory fits quite good. So we can, of course, do more. So we can vary the photon energy. With that, we vary the perpendicular momentum. So we can take constant energy maps at various photon energies corresponding to various normal momentum values. In the end, we have this Brillouin zone here. So first I showed you results for this gray plane here. Now we move this plane of detection towards the gamma x direction, as what is here in the edge? The gamma m direction, in the perpendicular direction here. We can somehow map this together. By concatenating this data, we get a three-dimensional intensity array. And in principle, we simultaneously measure all binding energy. So we have a four-dimensional data array where we can take sections as we want. For example, we can plot the Fermi surface here of ruthenium dioxide. And we can now also take cuts in other planes if we want. So, but now let's dwell a bit on the Fermi surface of ruthenium dioxide, because this Fermi surface here is indicative for the magnetic structure. So if you do the calculation in the paramagnetic case, the Fermi surface should look like this. If you do the calculation with the altermagnetic electronic structure, you expect a Fermi surface like this, and this fits much better to our experimental value than this paramagnetic calculation. So these were experiments at the synchrotron. We can do experiments also in our lab using laser excitation. In this case, we excite photoelectrons by just 6.4 eV. This is very good for practical reasons because you can use the fourth harmonic of a titanium sapphire laser. And this gives you the opportunity to do these experiments in the lab. And there is a drawback, of course. You will have a limited field of view in momentum space. That is depicted here. So here's the gamma point, zero momentum. Now you excite electrons with a 6.4 eV. This corresponds to a momentum vector here for excitation. With 6.4 eV for this ruthenium dioxide, you just happen to hit the gamma point in the next adjacent Brillouin zone. But you have only a certain angular acceptance angle, and that means you can only detect electronic states near the gamma point. This is shown here. So here this is the intensity map, and we just see something from this one band here at the edges of our field of view. But you see here nicely the dispersion. This is the gamma m direction, so the red line, which is hard to see here, corresponds to this figure. So the gamma m direction, which was our interesting direction, shows this dispersion here, so this we can see. The method at 6.4 eV has some advantage against this usually helium lamp excitation that one does in the lab, because it's less surface sensitive, you get a high intensity, and you can have a quite high energy resolution with that. Now we repeated the experiment, also circular dichroism. So we measure the intensity distribution for circular right and circular left. We calculate the asymmetry, so difference of those two divided by the sum. This gives here, again, with the same color code, blue means negative asymmetry, red means positive asymmetry. And what we do see here is this asymmetry, which we then decompose in the anti-symmetric circular dichroism in the angular distribution, and then we finally also detect this magnetic circular dichroism that you can see here. So also for this sample, we observe a magnetic circular dichroism here, which clearly shows up, and as a test that this is not just a let's say an artifact of our measurement, we repeated the experiment with the light now shining at 90 degrees here, so perpendicular to the magnetization direction of the sublattice magnetization, if you want. And in this case, you see that the magnetic circular dichroism component vanishes. So this is as we have expected. So now I come to my summary. So this you remember, I started my talk with that. The ferromagnet will have a compensated magnetic moment, the antiferromagnetic not. And the question is, can we see the circular dichroism here? And hopefully I convinced you that we can indeed observe now the magnetic circular dichroism in our samples with two different methods, basically. We measured the magnetic circular dichroism with 6.4 eV and also in the range of soft X-ray excitation, 660 eV. The magnetic circular dichroism is consistent with calculations of the photoemission intensities. And the magnetic circular dichroism is related to the spin splitting of the states in the ruthenium dioxide. And with that, I'd like to thank you for paying attention to my talk. And this is part of the instrument that you can see here. Thank you very much.